Okay, so I'll begin the lecture in a couple of minutes. So, yesterday, uh, in the first lecture of organic chemistry, we saw certain important concepts like types of covalent bonds. We have seen that there is a polar covalent bond and a non-polar covalent bond. We have seen polar molecules, non-polar molecules. We have seen ionic compounds, and in ionic compounds, what um, decides how much covalent character ionic compounds have, etc. We have also seen how to calculate the formal charges. Okay, we have also seen how to calculate the formal charges. Now today we'll see how to calculate oxidation states and hybridization also. Okay, suppose you have this water molecule. Now in water molecule, oxygen is bonded to two hydrogens and it has two lone pairs. Yesterday we have seen how to calculate the formal charge. What was the formal charge? We just counted how many electrons oxygen has. And in formal charge, while calculating formal charge, we assume that whenever you have a bond pair, one electron is shared by one atom and the other electron is shared by the other atom. That means electrons are shared equally by two atoms. That was the assumption. That means these blue electrons are with the hydrogen and yellow electrons are with oxygen. So total number of electrons that oxygen has is how much? 6. 1, 2, 3, 4, 5, 6. And how many electrons does oxygen has in its valence shell? 6, right? So it is supposed to have 6 and it has 6. That's why the formal charge is 0. Formal charge is 0. And then next, we have seen in OH minus. So OH minus, the structure of OH minus is this. And how to calculate the formal charge on oxygen here? I'll count the number of electrons: 1, 2, 3, 4, 5, 6, and 7. And one electron is with hydrogen. So there are 7. There are 7 electrons with oxygen, but oxygen is supposed to have only 6. So there is one extra. That's why formal charge is -1. Okay, formal charge is -1. That's why you write OH minus. You write OH minus. Clear? Then we have also seen H3O plus. We have also seen H3O plus. H3O plus. H3O plus has one lone pair and two bond pairs, right? Now I am counting how many electrons the oxygen hold. 1, 2, 3, 4, 5. And these blue are with hydrogen. So how many electrons in total does oxygen have? 5. 5, 1, 2, 3, 4, 5. So it is supposed to have 6, so there is one less, deficiency is 1. So formal charge is +1. That's why you write H3O plus. Clear? Now next I'll go to the oxidation states. How to calculate the oxidation states? Now this is formal charge. Okay, in formal charge we assume that the bonded electrons are shared equally. Bonded electrons are shared equally between two atoms, between the bond exists. But when you find oxidation state, the situation is different. I'll take water molecule again. I'll take water molecule again. Let me draw water molecule. This is your water molecule. So it has two lone pairs and two bond pairs. Now you divide the bond pairs. Okay, if there is breaking of this bond, okay, and if only one of the two atoms between which the bond is shared can take the electrons, okay, so who will take? So electronegativity of oxygen is how much? Electronegativity of oxygen is 3.5, and hydrogen is 2.1. Okay, hydrogen is 2.1. Now if I do a partition of electrons, that means I want to break the bond, and the condition is that only one of the atom can take the electrons. Who will take the electrons? Obviously oxygen will take those electrons, because oxygen is more electronegative. Okay, so now I will count these electrons with oxygen. So oxygen has how many electrons? 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has 8 electrons. So while calculating formal charge, I was assuming that, two electrons are shared equally by two atoms between which the bond existed. But here, what I am doing is, when I am separating the bond, when I am, you know, uh, breaking the bond, I am giving electrons to only one of the atoms between which the bond exists. So I will obviously give it to oxygen. Oxygen will grab the electrons if it wants to separate. Okay, so how many electrons does oxygen has? Total 8. How many it is supposed to have? It is supposed to have 6. It has 8, and it is supposed to have originally, oxygen has 6 electrons. So how many extra electrons does it have? It has 2 extra electrons. That's why oxidation state is -2. Oxidation state of oxygen in water is -2. Similarly, in OH minus, let us see. In OH minus, this is OH minus. So this has 3 electrons. Now I do the partition. Okay, so who will take the electrons? Oxygen will take the electrons. Now count total number of electrons on oxygen: 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what is the oxidation state of oxygen here? Again -2, because it has 8 electrons. It is supposed to have 6. So in OH minus also, oxygen has oxidation state of -2. Similarly, in H3O plus also, the of oxygen will be -2 only. So oxidation state of oxygen is always -2, unless, so if I do the partition, who will take the electrons? Oxygen will take all the electrons. So I will count all the electrons with oxygen: 1, 2, 3, 4, 5, 6, 7, 8 again. So there are 8 electrons, 2 extra. It is supposed to have 6, so oxidation state is -2 again. Okay, so in H3O plus also, oxidation state is -2. Does oxygen always have oxidation state of -2? Not always. There are cases where oxygen doesn't have oxidation state of -2. For example, in hydrogen peroxide is what? H2O2. This is the structure of hydrogen peroxide. Okay, this is the structure of hydrogen peroxide. Okay, one more thing you observe here. Here. Okay, I'll draw again. Before going to hydrogen peroxide, I'll draw it again. This is water. This is OH minus, and this is H3O plus. Now see, when oxygen has 2 lone pairs, it has 2 bond pairs. When it has 3 lone pairs, it has 1 bond pair. When it has 3 bond pairs, it has 1 lone pair. Let me write down. Here you have 2 lone pairs and 2 bond pairs. Here it has 3 lone pairs and 1 bond pair, and here it has what? 3 bond pairs and 1 lone pair. So you must remember this, and I'll talk about other things also. For example, let me talk. Okay, I'll just write them down again in a tabular form, so that you can understand. For nitrogen, for carbon, I'll give a pattern for you. Okay, anyway, before that, let us look at this hydrogen peroxide. In hydrogen peroxide, if I do the partition of electrons, uh, so I'm interested about this oxygen, so I'm doing the partition. Okay, when I'm doing the partition, this oxygen is attached to this hydrogen, and it will pull the electrons from the hydrogen, so it will include both the electrons here. But on the other side, it is attached to oxygen, which is equally electronegative. Okay, which is equally electronegative. So it will not take both the electrons, it will take only one electron, because the oxygen on that side is also of equal strength. So this electron comes with this oxygen, these two come with this oxygen, this comes, these are lone pairs anyway, which are with the oxygen. So total how many electrons is oxygen getting? 1, 2, 3, 4, 5, 6, 7. How many oxygen is supposed to have? It is supposed to have 6. Okay, but it has 7, it has 1 extra, therefore oxidation state is -1. Oxidation state of oxygen in peroxide is -1. Generally in oxide it is minus whenever you have peroxy bond. What is peroxy bond? Bond between oxygen and oxygen. Oxidation state is -1. Clear? So does oxygen has only two oxidation states, -2 and -1? No, it has 0 also. When will it have 0 oxidation state? In O2 molecule. Oxygen is bonded to oxygen. Whenever oxygen has two bonds, two bond pairs, it will have two lone pairs. Okay. Whenever oxygen has two bond pairs, it will have two lone pairs. Now if I do the partition, the oxygen will take only these two electrons. It will not take these two. It will not take these blue electrons. It will take only these green electrons. Why? Because it is attached to an atom which is equally electronegative. So these two green electrons plus these two lone pairs. Total how many? Total of 6 electrons it has. 6 electrons. How many it is supposed to have originally? 6. And it has 6. So there is no extra electron, or there is no deficiency of electron. That's why oxidation state is 0. Here oxidation state is also 0. Even the formal charge is also 0. Clear? Okay. Let me go to some other examples. Okay. Okay. Anyway, so let us talk about nitrogen. Okay, I'll write down oxygen first. So first let me write negative. So whenever it is OH minus, the structure is like this. Whenever it is water, the structure is like this. And whenever you have hydronium, positive charge, the structure is like this. So here see the pattern. One bond pair, three lone pairs, two bond pairs, two lone pairs, and here three bond pairs and one lone pair. You see, bond pairs are increasing and lone pairs are decreasing. Lone pairs are decreasing. Clear? And I will draw some other structures that you will need to remember. Okay. So nitrogen has, okay, let me draw the neutral thing in the middle. So I'll draw ammonia here. Ammonia, the structure is this. So this is the structure of ammonia. This is the structure of amide. Okay. Whenever you have negative charge, the names are like ide. This is hydroxide and this is amide. This is hydronium. And whenever you have structures or whenever you have cations, the names always end with em. So ammonium. So whichever things hold positive charge, their names are always ending with em. Whichever things have negative charge, their names end with ide. For example, Cl minus is chloride, Br minus is bromide, I minus is iodide. Here it is hydroxide and here it is amide. Okay, and whichever compounds, or which, sorry, not compounds, whichever ions have positive charge, their names end with em. Ammonium, okay, hydronium, or all the alkali metals, sodium, potassium, huh? Rubidium, cesium, they generally in nature exist in the form of cations. Okay, that's why their names, their original names are also sodium, potassium, rubidium, cesium, and francium. Similarly, calcium, magnesium, calcium, strontium, radium, all these things, their names end with em because generally in nature they don't exist in neutral form. But chlorine, bromine, iodine, in elemental form they can exist. That's why their names are not chloride, bromide, iodide, etc. Fluoride. They get that name when they acquire negative charge. Okay, in elemental form they can exist with zero. Anyway, let us write the lone pairs and bond pairs. Here you have two bond pairs and two lone pairs. Here you have three bond pairs and one lone pair. Here you have four bond pairs and zero lone pairs. See, look at the pattern again. Number of lone pairs are increasing. Sorry, number of lone pairs are decreasing and number of bond pairs are increasing. Okay, so you remember this rule that whenever oxygen has negative charge, it has three lone pairs and one bond pair. Whenever oxygen is neutral, it has two lone pairs and two bond pairs. Whenever oxygen has positive charge, which charge? Formal charge I am talking about. Whenever oxygen has positive charge, it has three bond pairs and one lone pair. And for nitrogen, whenever it has negative charge, like in amide, it has two lone pairs and two bond pairs. Whenever it is neutral, it has three bond pairs and one lone pair. And whenever it has positive charge, it has four bond pairs. So these will come again and again for you. Okay. Now let us talk about carbon. Let us talk about carbon. Now carbon generally has four bonds. For example, in methane, it has four bonds. Now it can either lose a proton, so it will leave this bond pair as lone pair and acquire a negative charge, or the hydrogen, instead of hydrogen, if there is some uh, atom like chlorine attached, when it leaves, it will not leave the electrons behind, it will take away the electrons because it is more electronegative. Okay, for example, if chlorine was attached here and it leaves, it will take away the electrons and it will leave positive charge, and there is no lone pair here. So here just look at this. If it has zero lone pairs and four bond pairs, it is neutral. If it has one lone pair and three bond pairs, it is having negative charge. Whenever it has zero lone pairs but only three bond pairs, it has positive charge. So these structures you have to remember. These structures for oxygen, the structures for nitrogen, the structures for carbon. Now here you can calculate formal charge and so on and so forth. But let me calculate oxidation state here. Here let me calculate see, we already did it for water, hydroxide and hydronium. Now let me do it for nitrogen. Okay, now here nitrogen, is it more electronegative than hydrogen or less? It is more electronegative. Nitrogen's electronegativity is how much? 3.0. Hydrogen's is how much? 2.1. Now if I do the partition of electrons, who will take the electrons? Nitrogen or hydrogen? Nitrogen will take. So totally how many electrons does nitrogen has? 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons. It is supposed to have 5 electrons, right? Nitrogen is supposed to have 5 electrons because its atomic number is 7. But it has 5 electrons. It has 8 electrons. That means it has 3 extra electrons. So oxidation state is -3. Here also, if I do the partition of electrons, who will take the electrons? Nitrogen, because it is more electronegative. So it gets 1, 2, 3, 4, 5, 6, 7, 8. So again 3 extra. Here again it's -3. Here also, when you do the partition, all the electrons will be grabbed by nitrogen. So 1, 2, 3, 4, 5, 6, 7, 8. So here also oxidation state is -3. Observe, oxidation state of oxygen was always -2 here, correct? But formal charge was -1 here. I'll write formal charge in blue color. Okay, I'll write formal charge in blue color. So formal charge was -1 here, it was 0 here, and it was +1 here, formal charge. Whereas oxidation state was always -2. Similarly, For nitrogen, what was the formal charge here? It was -1, and here it was 0, and here it was +1. So formal charge is calculated assuming that electrons are shared equally. Okay, but when calculating oxidation state, you give the electrons to the more electronegative atom and calculate. Now tell me, what is the oxidation state here? What is the oxidation state here of carbon? So who will take the electrons if there is a partition? Obviously carbon will take, because carbon's electronegativity is 2.5 and hydrogen's electronegativity is 2.1. So carbon will take all these 4 electrons. So how many electrons does carbon has? 1, 2, 3, 4, 5, 6, 7, 8. It is supposed to have 4, it has 8. So oxidation state is -4. Formal charge is 0. Okay, here again 1, 2, 3, 4, 5, 6, 7, 8. So it has 4 extra electrons. Formal charge is -4. But here it is 1, 2, 3, 4, 5, 6. So only 6 electrons come. So it has only 2 extra electrons. So here oxidation state of carbon is how much? -2. Okay. Let me give you some other examples quickly. You will understand. See, suppose you have acetylene. In acetylene, there is a triple bond between 2 carbons and it is attached to hydrogens. Then you take ethylene. So these are common names of these compounds: acetylene, ethylene, and then let me draw ethane. CH3, CH3. This is ethane. Okay. Now let me see, all the formal charges are 0 because this is a neutral molecule. Everybody knows there is no charge here, so nobody holds any formal charge. All the formal charges on carbon are 0. If you want, you can calculate formal charge. For example, if I do the partition, equally divide electrons, so how many electrons does carbon has? 1, 2, 3, 4. So it is supposed to have 4. That's why what? Formal charge is 0 anyway. Now let me calculate the oxidation state. So you can calculate the formal charge in of every carbon. It will be 0 only. You can check it. Okay. Now let me calculate the oxidation states. Okay. Let me calculate the oxidation states. Okay. Let me calculate the oxidation state. So for oxidation state, when I do the partition, so on that side you have carbon, so it is equally electronegative, so I have to share equally. But here I will grab all the electrons from hydrogen, so this electron also I will take from hydrogen. So totally how many electrons I have for calculating oxidation state? 1, 2, 3, 4, 5. So there is 1 extra, therefore oxidation state of carbon is -1. So oxidation state is -1 here. Oxidation state is -1. Let me calculate oxidation state here. So here when I do the partition, this will be equally shared because it is of equal electronegativity, but these electrons the carbon will totally grab. Okay, 1 second. Okay. So let us count total number of electrons. So this 1, 2, 3, 4, 5, 6. So there are total number of 6 electrons. So there are 2 extras. Carbon is supposed to have 6. Sorry, carbon is supposed to have 4, but it is having 6 here. So there are 2 extra electrons. So oxidation state is -2. Next, here, let me do the partition of electrons. So carbon will grab from hydrogen, but it cannot grab totally from carbon, so it will take only 1 for carbon because it is equally electronegative. So total number of electrons is 1, 2, 3, 4, 5, 6, 7. Total 7 you have here. So it is supposed to have 3, sorry, it is supposed to have 4, but it has 7, that means it has 3 extra. So that's why oxidation state is -3. Now what is happening? See, what is happening here? What is happening here? What is happening here? Oxidation state is decreasing. So reduction in oxidation number is called reduction. Reduction in oxidation number is called reduction. And if you go from here to here, oxidation number is increasing. See, -1 is greater than -2 is greater than -3. So here oxidation number is increasing. So this is oxidation. So one of the definitions of reduction is addition of hydrogens, and that is what is happening, addition of hydrogens here. So while you are adding hydrogens, what is happening? There is a reduction in oxidation number. Okay, and removal of hydrogens is called oxidation. Okay, so when you go from here to here, there is removal of hydrogens. Removal of hydrogens. So removal of hydrogens is also what? Oxidation. That's why oxidation number is increasing. Clear? So this is about oxidation numbers. So you have to be thorough with calculating oxidation numbers as well as formal charges. So formal charges you don't calculate actually. You know what the formal charge of any atom is by just looking at the molecule, because you will see those molecules again and again, and you will be pretty sure what the oxidation state is. Sorry, what the formal charge is. For example, in or H2O minus, but in hydroxide, formal charge on oxygen is -1. That's why you write OH minus. And in hydronium, formal charge on oxygen is +1. That's why you write H3O plus. And same thing for amide, ammonia, and ammonium. Okay, amide holds negative charge. That's why formal charge on nitrogen is -1. Ammonia is neutral, so formal charge is 0. And ammonium is positive, we write NH4 plus, so formal charge on nitrogen is +1. Clear? And moreover, when you talk about oxidation number of oxygen is always -2 whenever it is attached to some other atom other than fluorine. Of course, when it is attached to fluorine, it will have a positive oxidation state. So I asked you, will oxygen always hold negative 2 oxidation number? No, generally it holds -2 oxidation number whenever it is in the form of an oxide. But in molecular elemental form, O2 molecule, it holds an oxidation state of 0, and in peroxide it holds an oxidation state of -1. But when it is attached to fluorine, like OF2, oxygen attached to 2 fluorines, it will hold an oxidation number of +2. It will hold an oxidation number of +2. Let me draw OF2. So oxygen attached to 2 fluorine atoms. So this is molecule OF2. So whenever oxygen has 2 lone pairs, it has 2 bond pairs. Okay. Now if you do the partition of electrons, will oxygen take electrons from fluorine, or will it leave? It will leave, because fluorine is more electronegative. It cannot take. Okay. Whenever I do the partition based on electronegativities. So how many electrons does oxygen have now? 1, 2, 3, 4. How many it is supposed to have? It has 4. It is supposed to have 6. So it has 2 less. So there are 2 electrons deficient here. That's why oxidation state is +2 in OF2. Okay, that means oxygen can also have a positive oxidation state. But fluorine, here, if you look at the fluorine will grab that electron. So how many electrons does fluorine has? 1, 2, 3, 4, 5, 6, 7, 8. It is supposed to have 7, but it has 8. Okay, supposed to have 7, but it has 8. So it has 1 extra. So fluorine holds -1 oxidation state here. Okay, fluorine generally holds -1 oxidation state. Fluorine generally holds -1 oxidation state, except in its elemental form. Elemental form is fluorine attached to fluorine. Here it will bear Zero oxidation state. You know why? Just do the partition. So this will be shared equally because on the other side also you have fluorine. So 1, 2, 3, 4, 5, 6, 7. Total 7. So it is supposed to have 7 and it has 7. That's why oxidation state is 0. Oxidation state is 0. Clear? Okay, this is about all about oxidation states. You have to be clear by now about oxidation states. Now, next we'll talk about hybridization. How to see what the hybridization is. There are certain complications when you have resonance. I will discuss about that when I discuss aromaticity, but now I am discussing only simple molecules. Okay, suppose you have molecule like this, CH4. So now here you count how many bonds and how many lone pairs are present. So lone pairs are 0 because there are no lone pairs. And how many bonds are there? 1, 2, 3, 4 bonds. So there are total 4 groups attached to it. 4 groups attached to it. What are the 4 groups? 4 bond pairs. So hybridization is sp3. Okay. Now here, for example, in some other molecule like ethane, let us see. Let us look at ethane one by one. Let me explain. So I wish to calculate the hybridization of this carbon, this yellow carbon. So see how many groups are attached. There are no lone pairs, so leave. But there are 4 bond pairs, so there are 4 groups attached. That's why it is sp3. Clear? Next, look at this. This is ethene or ethylene. Now I wish to calculate the hybridization of this carbon of this yellow carbon. Now how many groups are attached? Is there any lone pair? There is no lone pair, so leave that. So there are 3 bonds attached. Don't look at double bond. You just count the sigma bonds. Don't count the pi bonds. So 1 sigma bond, 2 sigma bond and 3 sigma bonds. So there are 3 groups attached. So 3 groups, if you have 3 groups attached, then hybridization is sp2. See, whenever you have 4 groups attached, hybridization is sp3. S, P, 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 P. This is sp3. 4 groups. Okay. Whenever 4 groups are attached, hybridization is sp3. Whenever 3 groups are attached, hybridization is sp2. These are, 3 groups. Now let me go to the next molecule. Carbon triple bonded to carbon and then attached to hydrogen. Here, how many groups are attached? I am interested to find the hybridization of this carbon. So there is no lone pair. Leave it. So there is 1 group and 2 groups. I don't count pi bonds. I count only sigma bonds. So there are 2 groups attached. 2 groups attached. So hybridization is sp. So S and P, 2 groups. Clear? Now let me go to some other molecules which have lone pair. For example, OH2 or H2O, water. How many groups it has? This is first group, 1 lone pair, 2 lone pair and 2 bond pairs. So 4 groups. 4 groups implies sp3. The hybridization state of this oxygen is what? sp3. Okay. Let me draw one more. NH3. This is what? Ammonia. How many groups it has? Let me count. 1 lone pair and 3 bond pairs. So 4 groups. So this is sp3. Next. Let me see this. This is amide. NH2 minus. So amide NH2 minus is like this. Okay. So negative charge is on nitrogen. Formal charge on nitrogen is minus. So how many groups it has? Again, 1 lone pair, 2 lone pair, 1 bond pair, 2 bond pair. Total 4 groups. 1, 2, 3, 4. So this also has hybridization of sp3. Clear? What about carbanion? What about carbanion? Carbanion has 3 hydrogens and 1 lone pair, right? Okay, 1 second. The screen is not visible. So it's disconnecting in between. I don't know why. So whenever it disconnects, you just send me a message or give me a call on WhatsApp. It is better because uh, if you send me a message, I may or may not see. You can just give me a ring. Okay. So whenever screen goes off, you can give me a ring. I'll just check it. Okay, because I'm looking into the iPad and uh, doing. So I'm just fixing it now for now. Okay. Okay. Okay, let us talk about carbanion. Carbanion has how many groups? Carbanion has how many groups? It has three groups, three bond pairs, one, two, three, and one lone pair. So four groups. So here also hybridization is sp3. 1 second. I don't know why this is disconnecting. Let me just. Okay, let me just try to get back. Yeah. Okay. So this carbanion has one lone pair and three bond pairs. One lone pair and three bond pairs. So total four groups are present. That's why hybridization is again sp3. Clear? Now next. What about carbocation? What about carbocation? Let me draw a carbocation. Carbo has three bond pairs and zero lone pairs. Zero lone pairs. Negative charge. Okay. What is the hybridization here? Let me count the total number of groups. One group, two groups, and three groups. There are only three groups attached. There are no lone pairs. That's why hybridization is sp2. So hybridization of carbocation is sp2. Okay. So just if the screen goes off, just give me a call on WhatsApp. I will just check it. Okay. Just give me a call. Okay. Anyway, so this is about hybridization. Okay. Now, one more thing you need to remember about hybridization is if p character is more, the orbital is longer. The hybrid orbital is longer because p is a long orbital. If s character is more, orbital is shorter because s is a spherical orbital. So the character of s is, more. For example, in sp, there is more s character, so orbital is very short. In sp2, a little bit uh, extra p character you get compared to sp in sp2, so orbital becomes little bit longer, and in sp3 p character is further more, so the length of the sp3 orbital is biggest among the three. So let me just write it down. Actually, in sp p character is 50%, in sp2 p character is, I think, 67%, right? And in sp3 p character is 75%. So this is p character. P character. So SP will be little bit short like this, SP2 will be little bit longer, and SP3 will be longest. Okay, this you keep in mind. It will be useful later when you study, about acid strengths of various compounds. Okay, so this is about, what? This is about hybridization, how to look at the hybridization. There is some complication when you look at the hybridization of aromatic compounds. I will come to that later. There resonance is involved, and we look at the localization, if electrons are localized or delocalized, whether to count them or not to count them. That's a little bit advanced topic, not advanced topic, but the topic comes later. But for now, you have to be able to calculate the hybridizations of these simple molecules. Okay. Now, what did we study? We studied how to calculate formal charge. We studied how to calculate formal charge. We studied how to calculate oxidation state. We studied how to calculate hybridization. Clear? Okay, fine. Now let me go back to the PDF. Let us see what do we have in our PDF. So hybridization. Okay. Now is discussing various types of hybridization. When you have sp3 orbital, there is one s orbital and there are three p orbitals in that hybridized orbit, hybridization, involved in hybridization. So the number of leftover p orbitals will be 0, because see, in the first orbit there is one s, there is no p, and in the second orbit, we are talking about carbon in organic chemistry, that's why we are talking about second orbit, there is one s orbital and there are three p orbitals, okay, px, py and pz. Now, if all the p orbitals are participating in hybridization, unhybridized orbitals are 0. So in sp3 hybridization, you don't have any unhybridized orbitals left. You need to remember that. In sp2 hybridization, only two p orbitals are involved. So one unhybridized orbital is what? Number of unhybridized orbitals are how many? 1. Whereas in sp, only one p orbital participates in hybridization. So the number of unhybridized orbitals is 2. Okay, and the geometry of the orbital of sp3, hybrid orbitals is tetrahedral. They are pointing in 4 different directions in space, so it is of tetrahedral structure. That's why methane is also tetrahedral, because the carbon in methane is what? sp3 hybridized. Now, why did they propose this hybridization? Actually, they proposed this because when they looked at the bonds, 4 bonds of uh, methane, which in which carbon is attached to hydrogen, if there is no hybrid, if there is no hybridization, 3 bonds should be identical and 1 bond should be different, because there is one s orbital and there are 3 p orbitals. So actually, what should you expect? You should expect that one bond which is formed from s orbital to be different or shorter or stronger, whatever it is, from other 3 bonds which are formed by the sharing of electrons from p orbital. But in fact, when you do NMR spectroscopy, it turns out that's a method with which you can look at the bonds and how the length of bonds are, how the strength of bonds are. Scientists found out that all the 4 bonds are exactly identical, so that means there should be something happening. So they proposed this theory called hybridization, that all these 3 orbitals and 1 s orbital, they mix up and they form 4 equal orbitals. That's why 4 bonds are same. Anyway, okay, what is the angle between 2 bonds in CH4? It is 109 degrees 28 minutes. 28 minutes is what? Approximately 30 minutes. 30 minutes is half degree. So it is 109.5 degree. The orbitals containing each pair of electrons are neither purely p or s. They have both the characters of p and s. That means they are hybrid of p and s. Since we are hybridizing one s orbital and 3 p orbitals, we call it sp3 hybridization. Okay, so this is how sp3 hybridized orbitals are. Now s is spherical, px is along x-axis, py is along y-axis, and pz is along z-axis. But they mix up and they form 4 new orbitals which are in the direction of a tetrahedron. Okay, so even the directions change after hybridization. The direction, see, s has no direction because it is spherical. Okay, but p is in the direction of x, y, this px is in the direction of x, py is in the direction of y, pz is in the direction of z. So the angles between these 3 orbitals was originally 90 degrees, but after hybridization it is not 90 degrees. After hybridization, 4 new orbitals form, s is gone, px, py, pz are gone, and these 4 new orbitals, they are orienting, they orient themselves in the direction of a tetrahedron. So angle between every orbital is 109 degrees 28 minutes. If you take any 2 orbitals and measure the angle between them, it will be 109 degrees 28 minutes. Okay, now this is like CH4. The example of sp3 hybridization is carbon in CH4. So all the angles, if you measure, they all measure to be 109 degrees 28 minutes. Even the molecules of NH3 and H2 are sp3 hybridized. We have just seen. Why? Because nitrogen has 4 groups attached, so it is sp3. Okay, so but the angle is not 109 degrees 28 minutes because lone pair bond pair attraction is more than bond pair attraction. So these bonds come little bit closer to each other, so angle is reduced from 109 degrees 109.5 to 107.5. Clear? Okay. Now whereas in water you have two lone pairs, and you know that lone pair repulsion, lone pair repulsion is more than lone pair bond pair repulsion is more than bond pair repulsion. Why? That is again topic in chemical bonding, so I'm not going into that. So because of this there will be more repulsion and these bonds will come further. This is a little bit irregular because it is not in the natural angles, so angles are little bit changed. So this tetrahedron, if we consider these lone pairs also, it's a tetrahedron. So here also angle is little bit less, so it is a distorted tetrahedron. Now sp3 hybridized. In sp3 hybridization, the shape is trigonal, 2 p orbitals and 1 s orbital. 2 p orbitals and 1 s orbital. See, last time this was 3-dimensional because sp3 was 3-dimensional because we had p in x direction, y direction and z direction. So it is in space. So the resultant orbitals are also 3-dimensional. Tetrahedron is a 3-dimensional structure. But here in sp2 what happens? In sp2 only px and py participate, pz doesn't participate. Now xy is in xy plane, s is anyway not having any direction. So if you consider these three, s, px and py, they should lie. Hybridized orbital will be in one plane and it will be having a trigonal planar structure, and perpendicular to that plane will lie pz. Perpendicular to that plane will lie pz. So here, if you look at the structure of sp2 orbital, it is in a plane, and above and below the plane this unhybridized orbital is there. So for example, in BH3, the hybridization is sp2 and this pz orbital is perpendicular to the plane containing the bonds, even in plane, and their shape is trigonal planar, and the unhybridized pz orbital will be perpendicular. This, what is this molecule? This is molecule of ethene or ethylene. Okay, so it is called a banana bond, one from above and one from below. Anyway, so this molecule also lies in one plane, and unhybridized orbital is perpendicular to the plane, and there is a pi bond because of which this will bend like this. Okay, anyway, let us look at sp hybridization. Now sp must be linear. You know why? Again, diagram. In sp only s and px participate. Now px has only one direction, right? X direction. These two are perpendicular to x. Y is also perpendicular to x. Z is also perpendicular to x. sp hybridized. sp hybridized is linear. For example, this is the structure of acetylene. This is the structure of acetylene. Carbon-carbon triple bond. So there will be one banana bond above, one banana bond below, one banana bond in front, and one banana bond on the back. So this is the x direction. Okay, and above and below is y direction, and front and back is z direction. Okay, so this is sp hybridized. Okay, sp orbital is always linear, and this is BeCl2. This is also sp hybridized, and these two lobes that you are seeing are unhybridized. So this will be in x direction, one will be above and below, that is in y direction, one will be perpendicular to the page, that is z direction. Is it clear? Okay. Okay, anyway, okay, yesterday we discussed something about boiling points, and I discussed only alkanes, and I discussed also about what? I also discussed about what? Melting points also. I discussed about melting points also. Now before going back to this, let me discuss few more things, very important things. Uh, Yesterday I talked about solubility, right? I told you that ionic compounds are soluble. Ionic compounds are soluble in water. And if covalent character is increasing in ionic compounds, according to Fuzzen's rule, you can check, then solubility in water will little bit decrease. Okay. So anyway, that's a general observation or some periodic trend, you can say. There will be exceptions in inorganic chemistry. I don't disagree. There will be many exceptions, but we are not going into exceptions. I'm just talking about a general rule of thumb. Okay. Now, I told you why NaCl dissolves. Na is positive, holding positive charge. Cl holds negative charge. So this is Na, and this is Na plus, and this is, okay, let me write little bit away. So this is Na plus and this is Cl minus. And they are, when they are in their crystal form, Na is surrounded by Cl and Cl is surrounded by Na. And in water they separate because sodium will say that I am getting negative charge from water, so I don't need you anymore. Okay, and it will separate. So it will separate. So all the oxygens in water molecules will surround this sodium three dimensionally, but I cannot draw three dimensions here, so I'm drawing only two dimensions. So they will be on the top and bottom of the screen also. And here, okay, chlorine will say no problem, you are getting negative charge from oxygen, no problem, I am getting positive charge from hydrogen, and both of them will separate. And that's why I told you what ionic compounds dissolve in water. That's why NaCl dissolves in water. And even some covalent compounds dissolve in water. Which covalent compound dissolve in water? Polar covalent compound dissolve in water. Polar covalent compounds also dissolve in water. You know why? For example, what is the best example of polar covalent compound? Best example is HCl. HCl. In HCl, chlorine is more electronegative, so it holds partial negative charge, and oxygen gets partial positive charge. So this will obviously dissolve in water. Why? Water can attract this. Why water attracts this? Because water has partial negative charge on oxygen, which is attracted to this hydrogen, and it has partial positive charge on hydrogen. Okay, partial positive charge on hydrogen, so it is attracted to chlorine. So that's why HCl dissolves in water. And generally when you look at hydrochloric acid, it is actually a solution in water, 0.1 molar, 1 molar, 0.5 molar, and so on. So generally you have HCl dissolved in water. Why? Because it is a polar solvent, it is a polar compound. Polar compound or polar molecule. So all polar molecules dissolve in water. More the polarity, more the solubility. More the dipole moment, more the solubility. More the dipole moment, more the solubility. Correct? So more polar the molecule is, more it is soluble in water. And there is one more reason for certain compounds dissolving in water. Okay. For example, glucose dissolves in water. If you look at the structure of glucose, it is something like this, or I can say any monosaccharide, or I can say any monosaccharide with 6 carbons. So what is the structure of glucose? It has, glucose, mannose, allose, idose, all these six-membered sugars, 6 carbon sugars. They will have OH attached. So this is not exactly the structure of glucose. It may be the structure of mannose. It may be the structure of, okay, so CH2OH. So whatever it is, so any sugar like glucose, mannose, all these sugars dissolve in water. You know why? Because they have alcohol groups, so many alcohol group. This is one alcohol group, two alcohol, three alcohol, four, you know 5 alcohol groups are there. Now whenever hydrogen is attached to oxygen, it forms hydrogen bond, and water also forms hydrogen bond, right? So this hydrogen, is attracted towards water because this water has lone pairs, and this hydrogen is attracted to this lone pair. So basically you have hydrogen molecule, OH groups attached to a molecule, hydrogen bonds, and whichever forms a significant number of hydrogen bonds, it will dissolve in water. For example, alcohol, CH3OH, dissolves in water because it can form hydrogen bond. Ethyl alcohol, C2H5OH, also dissolves in water because it can form hydrogen bond. Okay, HF dissolves in water very well. It dissolves more than HCl. The solubility of HF is greater than HCl. You know why? Because it can form hydrogen bonds. Okay, and ammonia also dissolves in water. Ammonia is a gas, but it can still dissolve in water. Actually, you pass ammonia through, if you pass any gas containing ammonia. Suppose in air you have ammonia. For example, in factory you are producing, you know uh, waste products in the form of some gases which contain air as well as ammonia. So what you do is you send this air containing ammonia through water, you bubble it through water. So water will absorb all the ammonia in it and it will purify it from ammonia, because ammonia is considered to be a pollutant. Okay, why is water able to take out or filter ammonia from that gas or from that effluent or whatever that stream of gas is? Because it is capable of forming hydrogen bonds. So ammonia will be dissolved in water. Okay, and this thing will dissolve in water, and C2H5OH also will dissolve in water. Okay, and if you look at the structures of certain things, let me show you what I'm talking about. Suppose you look at the structure of vitamin C. If you look at the structure of vitamin C, this is the structure of vitamin C. Okay, so this is the structure of vitamin C. On any website you can see. So you see OH groups attached to this molecule. That's why vitamin C is a water soluble vitamin. Vitamin C is a water. Okay, clear? Now if I search for vitamin A, if I search for vitamin A, this is the structure of vitamin A. Okay, this is the structure of vitamin A. So this is the structure of vitamin A here. This is the structure of vitamin A. Now notice the structure, there is one OH group. But the problem is that one OH group is not sufficient for dissolving this big molecule in water, because most of the molecule is non-polar, right? Most of the molecule is non-polar. So this OH alone has no, it can form hydrogen bond, but that one hydrogen bond is not sufficient. That one hydrogen bond is not sufficient for dissolving this big non-polar molecule into water. Non-polar substances don't dissolve in water. I'll just explain why. Okay, I'll just explain why in a minute. Now this was the structure of vitamin C. Okay, this was the structure of vitamin C. So this was the structure of vitamin A, vitamin C. Now vitamin C was soluble in water because it has so many OH groups and it can form so many hydrogen bonds. So that is causing it to dissolve in water. But vitamin A we have problem. Vitamin A we have problem because there is only one OH group, and that one OH group is not sufficient for us. Now why non-polar substances don't dissolve in water, I will explain. Suppose you have a non-polar molecule, say an alkane. Okay, so how many carbons you have? 1 2 3 4 5 6 7 8 9. I'll draw two more, 10 11 12. Okay, I'll draw total number of 12 molecules. Sorry, 10 11 12. So this is dodecane. This is dodecane. Dodecane is one of the components of diesel. Now you might have seen it doesn't dissolve in water. If you try to mix oil and water, they don't mix. Why? Because they don't dissolve. Why they don't dissolve? I'll explain. Because this is non-polar. This is non-polar. Why non-polar? Because all carbon carbon bonds are there, so there is no electronegativity difference, so it will not have any partial positive charges and negative charge. And electronegativity difference between hydrogen and carbon is also less, it's not much, 2.1 and 2.5. Even if there is, even if we say that okay, even if it is less, there is a difference, but because of the tetrahedral arrangements, all the dipoles will cancel. Because of the tetrahedral arrangements, because all the dipole moment is a vector quantity, all the dipole moments will cancel, and because of which, even if we say that CH bond is a polar bond, this molecule is non-polar because it has symmetry. The structure has symmetry everywhere. Every carbon is at the center of tetrahedron, so all the dipole moments of hydrogens around it will cancel. Okay, around it will cancel. So it is non-polar. So non-polar has no charges. Now when you try to mix them in water, the water will accumulate in one place and this oil will accumulate in the other place. You know why? Water has delta negative and delta positive charges. Okay, so one water molecule will attract the other water molecule, and all the water molecules, because one negative charge on one oxygen will attract the positive charge of the neighboring water molecules, and because of attraction between mutual attraction between all the water molecules will coagulate together, they come together, and oil will separate. Now depending on the density, if the oil is heavier, oil will settle at the bottom, water will settle at the top. If oil is lighter, oil will settle at the top and water will settle at the bottom. Depends on the density of oil. If you have heavy oil, it will settle at bottom. If you have light oil like kerosene, it will settle at the top of water. So oil and water don't mix. It's an adage in English. Oil and water don't mix. Okay, because the reason is, scientific reason is what? Oil is non-polar, water is polar. Polar and non-polar, they don't mix, they don't dissolve. Now that was the reason why vitamin A was not soluble. A had a big non-polar part. There was one small OH there which is incapable of dissolving. I'll explain what the reason in a better way. For example, if you look at alcohols, CH3OH dissolves in water. Okay, C2H5OH dissolves in water. Uh, this is methanol. This is methanol. This is the length of carbons is increasing. Now these three dissolve in water. Actually, these two dissolve very well. This thing dissolves partially. Okay, let me write it in yellow. This will dissolve partially. That means it will dissolve, but it will not dissolve in all proportions. It will dissolve in up to certain proportions. Beyond that, it will not dissolve. These will dissolve in all proportion. If you take half water, half alcohol also, they will dissolve. Okay, but these things will have difficulty in dissolving. And as the length of this carbon chain is increasing, as the length of this carbon chain is increasing, it will become more and more difficult for them to dissolve. That means if you come from methanol to higher alcohols. Okay, let me just check. The screen is gone again. Okay, so when I come from methanol to ethanol to propanol to butanol to pentanol, the non-polar part is increasing. So this is non-polar part. This is non-polar part, and this is the part that is polar or that is forming hydrogen bond. So when non-polar part was smaller, this hydrogen bond was managing for the solubility. It is managing the solubility of this molecule in water. When the length of that non-polar part is increasing, when the length of that non-polar part is increasing, the OH is not capable of dissolving that alcohol anymore. So what will happen is these two white color things will dissolve in all proportion, yellow color will partially dissolve, and from here it will become more and more difficult for alcohols to dissolve. In other words, alcohols start become oily from here. Oily means that doesn't dissolve in water. That is the reason why vitamin A was not soluble. That is the reason vitamin A was not soluble. Let me go back to vitamin A. So this was your vitamin C. This was your vitamin C. So it has so many OH groups. So many OH groups. That's why it can form large number of hydrogen bonds, and it is soluble in water. Whereas if you look at vitamin A, if you look at vitamin A, if you look at vitamin A, there is only one OH group. Rest of it is non-polar. That means that OH group is not capable of dissolving this vitamin A in water. That's why this vitamin is called, this is vitamin, that's why this vitamin is called, this retinol or vitamin A is called lipid soluble vitamin. It will dissolve in lipids or oils. It will not dissolve in water. Whereas water is called, sorry, vitamin C is called, vitamin C is called water soluble vitamin. This is water soluble vitamin. And vitamin A, vitamin A is what? Lipid soluble vitamin. Now there is one thing you need to understand here. If you take 10 tablets of vitamin C, nothing will happen because it is water soluble. If you take 10 tablets to you, because it is soluble in water, it will get excreted through your urine. Okay, but if you eat 10 or 20 tablets of vitamin A, you will probably get hospitalized. There will be poisoning or maybe death also, because body cannot remove that easily. Body cannot remove that easily. Why body cannot remove that easily? Because anything that dissolves in water can get excreted overnight, but anything that doesn't dissolve in water stays in your body for a long time. You have to remove them through other methods. Similarly, if someone consumes alcohol today, see, this is alcohol that people drink, alcoholic beverages. So the content, the substance that gives them whatever feeling they get is because of this ethyl alcohol inside it. It is mostly water, but it has ethyl alcohol. Now, if someone consumes ethyl alcohol, and if you test their body on the second day for ethyl alcohol, you will not find ethyl alcohol in their blood. You know why? It will be excreted overnight. But if someone takes some other drug, like for example THC, tetrahydrocannabinol, I am weak in spellings, but let me see. So tetrahydrocannabinol. Okay. Now this molecule is what? It is the main molecule in. It is the main molecule in what? They call it. I think cannabis, right? They call it cannabis, or they call it. I think weed. Okay. So this is the molecule that is responsible for that drug. Now, if you look at this molecule, mostly it is non-polar. There is one OH group attached to it. So what do you think of the solubility of this in water? It doesn't dissolve in water. Okay. So if someone takes this drug, and if you check their body after 7 days, this will still be in their body. Why? Because it is not soluble in water. It is not soluble in water, and it will not get excreted easily. Same thing about DDT. If you look at the structure of DDT, okay, if you look at the structure of DDT, if you look at the structure of DDT, this is DDT. So this DDT is used to DDT. So this DDT here, this is DDT. This is DDT. Now this DDT was used as a pesticide. They use it to kill uh, insects. They also use it to kill ants. They use it to kill mosquitoes. Okay. So when DDT was discovered during First World War, or between First World War and Second World War, at the time of the Great Wars, it was considered to be a miraculous chemical. Okay, even people like Winston Churchill mentioned these chemicals in their speeches, that they saved the lives of thousands of British soldiers or American soldiers from malaria, because they were very good at killing mosquitoes. But because this molecule is very non-polar, look at this molecule. This molecule will stay in your body. If it goes inside your body, it will stay for more than 30 years. That's why this is banned in countries of first world. This is banned in countries of first world. Like in the countries of USA and Europe, this chemical is banned. Okay, DDT is banned. In India, we still use it because this is a third world country, so we cannot afford other chemicals which are expensive. This is a cheap chemical and very effective chemical. That's why we still use it. Okay, we still use DDT. You go to any shop and ask for DDT, he will give you the powder of DDT, dichloro diphenyl trichloroethane. Okay. Anyway, so this is about solubility. Okay. Now, what do you do if you want to dissolve oil in water? Oil generally doesn't dissolve in water, correct? But what if you want to dissolve oil in water? For example, you have eaten an oily meal. Okay. You went to a restaurant and had a dish which was very oily. You have eaten it with your hands. Now, if you wash your hands with water, generally what happens, the oil doesn't go, because oil doesn't dissolve in water. So what do you use? You use soap. What are soaps? Let me show you what a soap is. Soap is called sodium salt of fatty acid. Okay, what is fatty acid? Any acid with long carbon chain. What is the general formula of acid? RCOOH. Okay, this is the general formula of acid in what? Organic chemistry. Okay, COH is an acid group. OH is a group of alcohol. I will discuss about this again when the chapters come, but this is just basic discussion. So if you know, it is good. If you do not know, don't worry. I will explain what the functional groups are, what acid group is, what amine group is, what alcohol group is, what ether is, what ketone is, what aldehyde is. I'll explain when the topics come. But now, so what is sodium salt? Sodium salt. When do you get salt? When a base reacts with acid, you get salt. So sodium salt of fatty acid is what? This. So when this reaction happens, you'll get RCOO minus and Na plus, and water comes out. This is neutralization reaction. Acid plus base gives you salt. So this is your soap actually. What is present inside soap? This RCOO minus Na plus, and this R will vary in different soaps. You can make soap with coconut oil. R has certain structure. You can make soap with olive oil. Soap has certain structure. You can also make soap with animal fats. So R will have these acids that you get from animal fats also. So anyway, this R is a long carbon chain. Fatty means what? I just told you. As the carbon chain is increasing, it is becoming more and more oily. Oily and fatty are actually similar words. They are synonymous. So fatty acid is what? Fatty acid. See, if you have something like CH3COOH, it is not fatty, or it is not oily, because it will dissolve in water, because it has hydrogen bond, COOH, CH3 COOH. So this will form hydrogen bond and it will dissolve in water. But what if this R group is, this is R group, right? If this R group is very long, what if this R group is very long? It will not dissolve in water. Why? Because there is only one OH group and there is a big non-polar part. So this is incapable of dissolving this long non-polar part in water. Okay. So now you have Na, right? So RCONA something looks like this. So this is a long carbon chain because it is a fatty acid. COO minus and Na plus. Now when you put this soap in water, Na plus will just go and dissolve in water, and these things will float in water. These all anions which have negative charge on one side and they are non-polar on the other side. So this yellow part is polar, and this blue part is what? Non-polar. This blue part is what? Non-polar. Now suppose you have oil. Now you have oil. Now oil doesn't dissolve in water because it is non-polar, but this blue non-polar part of soap, you know, will go and attach to that drop of oil. Why? Because non-polar and non-polar mix. So many soap molecules, the non-polar sides will go and surround this oil drop. Okay, they will surround from all directions, three-dimensionally. I cannot draw three-dimensionally. I'm drawing only two-dimensionally. Okay, but you understand that this is a three-dimensional structure, and on the outer surface of this three-dimensional spherical structure, you will have COO minus, COO minus, COO minus, COO minus, COO minus. So what do you get is a sphere. You get a sphere in which at the center you have this drop of oil. Okay, and that sphere on the outside is totally negatively charged. Now it can dissolve in water, and this is called a micelle. Okay, this is called a micelle. Okay, now this is capable of dissolving what? This is capable of dissolving oil in water. This is capable of dissolving oil in water. It will form a colloid. It will form a colloid. So that's why soap can dissolve oil in water, because soap forms micelles around that oil drop, and the center, even though the bulk of that micelle is non-polar, the outside surface is what? Negatively charged. That's why it is polar, and then it can dissolve in water, and then it can dissolve in water. Fine, good. Now this is the function of soap, and there is something in your body that acts as soap. For example, if you eat oily food, for digestion it should dissolve in water inside your stomach, but oil doesn't dissolve in water. So what acts as soap? You don't eat soap along with oily food, right? To digest that oil that you ate. So there is a natural soap inside your body that is produced by liver, and the name of that soap is, the what we call that soap is, you call that soapy substance bile salt. You call it bile salt. Bile salt is actually, bile salt is actually a kind of soap. Bile salt is actually a kind of soap. Clear? Your understanding? Bile salt is a kind of soap. Clear? Now bile salt is, one second. I think it is not connecting. Okay, let me check later. Okay, so bile salt acts like a soap for you, and it helps you in what? Digestion of oily foods or fats or whatever things that don't dissolve in water you eat. Okay. Anyway, next. So what's the duration of the lectures? It is 1 hour 19 minutes. One second, let me check. The screen isn't coming. Okay. Anyway, so give me a minute. I'll just check back. Okay. So let me switch the screen. Okay. Okay. Fine. I think there is some issue with the screen. I'll just check it. Is it visible now? Okay. I think it's visible. There was some issue. Okay, anyway, so this is about how soap works and what dissolves in water, what doesn't dissolve in water. And one more thing I want to say, these soaps or any substances that are like soap, for example, what did I say? Bile salt, they form colloids. They form colloids. What are colloids? Suspension of oil inside water. For that you need some colliding agents. Okay, uh, these are soaps. Soaps are the substances that are capable of forming your colloids. Now one more example of colloid is milk. You say milk contains proteins, milk contains sugars like lactose, and okay, lactose anyway dissolves in water because it is capable of forming hydrogen bonds just like glucose. Okay, but milk also contains fats. Now fats are like oily, right? They are non-polar substances. Fats are non-polar substances. Now if fats are non-polar substances, how are they dissolved? They are dissolved by some soap-like materials that are present in milk. They are called emulsifiers, emulsifying agents. So milk is an emulsification. Or if you have any oil mixed in water, that mix is called an emulsification. Now we call it emulsification of fats in water, and it is done by soap-like agents. Now milk is an emulsion. Milk is an emulsion. Now that's why when they churn milk, okay, you have seen how they make butter, right? They hold a centrifuge in their hand and they rotate that. Okay, between the hands, they rotate it. So what happens is these structures, these micelles, they break off because of that churning. So when they break off, when the structures break off after churning, when the structures break off, what will happen? The structures break off because of churning. So because of that force of churning. So what happens is this oil will separate from this micelle and it will come out of the milk. That's what butter is. And the milk that is left after this butter separates is called I think it is called skimmed milk, right? I think it is called skimmed milk or low fat milk, they say. Okay, so you have whole milk which has all these emulsifications intact, and when you churn the milk and remove the butter because of the breakage of these all micelles, the milk left is called a skimmed milk, and the butter separates and they sell butter separately and they sell skimmed milk separately. Okay, it is also called low fat milk. Okay, anyway, so this is about solubility of substances, and this is very important because based on this there will be questions in exam directly or indirectly. He may ask you directly or he may ask you indirectly also. Okay, and not only from exam point of view but from general point of view, any student of science or say any educated person is supposed to know all these things: how soap works, why oil doesn't dissolve in water, why salts dissolve in water, why glucose dissolves in water, so on and so forth. Okay, so I think end the lecture here. I think what's the time? It's only 1 hour 24 lecture here. I think what's the time? It's only 1 hour 24 minutes. So anyway, I will continue with a bigger lecture tomorrow. I will start little early, maybe at 8 o'clock, and I will take 2 hour or 2 hour plus lecture in the next class. And we will do some questions related to the concepts we have learned from the material. Okay, I'll post the material in the group. Okay, let's meet tomorrow. So initially I'm going a little bit slow, but as you know a few topics get finished, I will increase the speed and I'll try to speed up the lectures and end the syllabus in time, hopefully. Okay, now I'm ending the lecture. Thanks for watching.